Okay, so what I am going to do today is so the first thing I want to do is to give the proof that there are no global regular functions that are non-constant on a projective variety. Okay, in other words, on a projective variety the only global regular functions are constants. Okay, so so let me tell you a couple of things. First thing is that it's this result should be thought of as an analog or part of a general philosophy of results which say that on compact objects you don't have any the only global nice functions on compact objects are constants. Okay, so for example one such example is, for example if you take suppose you take the Riemann sphere, okay, namely the ordinary real sphere S2 and make it into a Riemann surface, which means what you do is to make it into Riemann surface you just have to be able to talk about holomorphic functions at a point or analytic functions at a point, and for that you use a stereographic projection to identify the complement of a point with the plane, and by taking two different points you can cover the sphere by two planes, okay, by the stereographic projection, and you can check that you can use this to define what is called a Riemann surface structure on the sphere, and then you can define what is then you can look at global holomorphic functions on the Riemann sphere, and then it will turn out that the only global holomorphic functions on the Riemann sphere are constant. The reason being that the Riemann sphere is compact, because it's, after all, topologically it is compact, it is a sphere. It's if for example if you want, it is both closed and bounded, so it is compact, and any global holomorphic function on the Riemann sphere, if you restrict it to the complement of a point, then you will get a holomorphic function on the plane, okay, and its image will be bounded because the image is compact, okay, so you get a holomorphic function, an entire function which is bounded, and Liouville's theorem will tell you that it is constant. So what will happen is that your holomorphic function on the Riemann sphere, if you throw out a point in the complement of a point, it will be a constant, and therefore by continuity it will also be a constant at that point, so it will globally reduce to a constant. Okay, so this is, for example, in tune with the general philosophy of results that says that whenever objects are compact, then the only global good functions on such objects are constants. Okay, you cannot expect non-constant good global functions on objects that are compact, and the fact is that in algebraic geometry the correct analog of compactness is projectivity. In fact, more generally the correct analog is called completeness, okay, but I won't be explaining about that probably in this course. I don't know whether I will do that, but you will come to know if you take second further courses in algebraic geometry. But I want to tell you that you must always think of projective varieties as compact, as the correct analogs of compact objects, okay, and the usual compactness doesn't make sense, I mean that doesn't give you anything special in Zariski topology, because you know Zariski topology is already compact. I mean that's the reason why we use the word quasi-compact. In fact, compactness in the sense that every open cover has a finite subcover, that compactness in algebraic geometry for the Zariski topology is renamed as quasi-compactness, okay, and it just comes free of charge. I mean it just comes free, okay. So there is nothing special if you define compactness to be just every open cover admitting a finite subcover. So you don't get anything, I mean there is nothing to, that is not a condition because it is always true, alright. That is the reason why the usual definition of compactness is of no use in algebraic geometry, and therefore it is redesignated as quasi-compactness, and therefore you can ask what is the correct analog of compactness. The correct analog is being projective, okay, at least when you study varieties, but the more perfect answer would be that the correct analog is that you should look at what are called as complete objects, okay, and projective varieties are examples of complete objects. So this is one fact. I am going to prove that, I mean we are going to show that on a projective variety the only global regular functions are constant. Then the other thing that we are going to show is the other thing that one has to be worried about is the following. See, if global regular functions are constant, then how do you study the object, okay. There are no global regular functions of the object, then how do you study the object? Now it presents a problem, because you see in the case of affine varieties the global regular functions they give you the affine coordinate ring, and you know the affine coordinate ring is an invariant, okay, it describes the affine variety completely, okay. In fact if you give me from the affine coordinate ring you can get back the affine variety by just taking the maximal spectrum and putting the Zariski topology on it, okay. Therefore for an affine variety the affine coordinate ring is the same as global regular functions, and that completely captures the affine variety, but it is not true for projective varieties. For projective varieties, first of all global regular functions are constants, okay, so there are no non-constant global regular functions. The second thing is, if you take the analog of the affine ring you will get the homogeneous coordinate ring. The homogeneous coordinate ring is also will not characterize your projective variety. So in fact the homogeneous coordinate ring will depend on the embedding, okay. So if you change the embedding into a projective space, if you take the same projective variety, okay, and put it in a different projective space, then the homogeneous coordinate ring will change. It will not be this same up to isomorphism. So you cannot keep track of the projective variety so easily, just either using regular functions, because there aren't any non-constant regular functions, and you cannot use the homogeneous coordinate ring to track your projective variety, okay. Therefore the only way of studying projective varieties is to study embeddings into projective space, okay, and this leads to the study of morphisms into projective space. The so called classically it was done by studying what are called as linear systems, and then and things like that, and in modern language we study line bundles and things like that, okay. So but these are all things that you will come across probably in a second course in algebraic geometry, but so what I want to say is that the fact that there are no non-constant regular functions on a projective variety, and the fact that the homogeneous coordinate ring of a projective variety does not characterize a projective variety, leads you to study embeddings of projective varieties into different projective spaces, and the embeddings are they need to be studied carefully, okay. So anyway, with that preamble, let me start with the theorem that we want to prove. So here is the theorem. If Y is a projective variety, then O of Y is equal to K. So in other words, every global regular function on Y is a constant, okay, where when I write K I mean every element of K is a constant, and it is thought of as the constant regular function. Constants are of course regular functions, okay. So what is the proof? So the proof is proof is a few ideas from commutative algebra and module theory, but I will explain that. So your situation is like this: you have Y which is sitting as an irreducible closed subset of some projective space. Of course we are always as usual working over small k, which is an algebraically closed field, okay, and you know what then you also have, so this diagram, if you go to homogeneous coordinate rings, it translates to a quotient. So closed subsets always correspond to quotients in algebraic geometry, and of course going to open subsets corresponds to going to a union of localizations if you want, okay. So so this is the polynomial ring in n plus 1 variables. You know, this is the affine coordinate ring of the affine space which for which the corresponding punctured affine space sits above this projective space. This is the quotient of the punctured affine n plus 1 space, okay, and that affine n plus 1 space has affine coordinate ring equal to this, and that affine coordinate ring is defined to be the projective homogeneous coordinate ring of the projective space. And then this closed, y being a closed subset of that corresponds to a quotient, you go modulo the ideal of y, so I put a subscript h, this is the homogeneous ideal of y, namely it is all those homogeneous polynomials which vanish on y, okay, and then you get sy. So sy is just spn mod iy, and of course the fact with all these things is that everything is graded, okay. So there is a gradation here, you know, the gradation here just corresponds to every polynomial being broken down into its homogeneous parts, okay, and and therefore you also get a gradation here, and the gradation here is just gradation when you read it mod iy, okay. So well now what one does is that we have already seen that, you know, if you take the so you know you have, so we have a picture like this, we have oy, this is the ring of regular functions on y, global regular functions on y, and of course k sits inside this as constant, as the constant functions, okay, because every scalar is being thought of as a regular function which is equal to that constant scalar, right, and then oy goes into ky, is the function field of y, okay, that is what we discussed and studied in the last lecture. And what is this function field of y? This is actually, we calculated it for a projective variety and we showed that you take sy, okay, you take homogeneous localization at 0, okay, 0 is a prime ideal, okay, the 0 ideal is a prime ideal because it is an integral domain. Even here you take the 0 ideal here, it is a prime ideal because this is an integral domain, you have only gone modulo iy, and iy mind you is a homogeneous prime ideal, okay, and the reason why iy is a homogeneous prime ideal is because y is irreducible, alright. So since you have gone modulo prime, this is still a domain, the 0 ideal is prime ideal, so you take the homogeneous localization at 0. So I want you to distinguish between this and the homogeneous and the non-homogeneous localization. So this sy sub 0, this 0 here, I don't put a round bracket around that 0, see this 0 is, you invert everything outside 0, okay, this is actually the quotient field of sy, this is the quotient field of sy, okay. So this consists of literally taking quotients of two polynomials in sy. Of course by a polynomial in sy I mean every polynomial in sy is some polynomial here read mod iy, okay. Of course here iy is the same as iy sub h, okay, I keep putting this h sometimes to just remind you that it is a homogeneous ideal, right, it is generated by homogeneous elements. So this is the quotient field of sy, but this is different, see this is homogeneous localization. So what you do is you don't, here you invert everything that is not 0, but here you invert only those things that are not 0 and which are homogeneous, okay, and the reason why you do that is when you do it like that, then you know this consists of elements of the form numerator by denominator, the numerator coming from sy and the denominator being a non-zero homogeneous element, okay, and therefore if the numerator is also homogeneous, since the denominator is also homogeneous, the difference in the degree of homogeneity will give you a degree, so this will become graded, this will be graded, and for this graded you take the degree 0 part. That is precisely the function field of ky. That's what we proved in the last lecture, right? So I'm just telling you, I'm just recalling that this is ky, the function field of y is actually this homogeneous degree 0 part of the homogeneous localization at 0, alright, which it sits inside this huge field. This is a huge field, this is the full quotient field of Sy, okay, and of course you must remember that this is, so you see Sy is sitting inside of course this is the, after all this is the quotient field of this integral domain, this sitting inside that, and what I'm going to do, I'm going to do the following thing. I'm going to start with an f here, I'm going to start with a global regular function on y, so f is a global regular function, f is from y to a1, it's a morphism. A global regular function is a regular function is just a morphism into a1, okay, we have seen that before. So this f is a global regular function, it's defined on all of y and it takes values in a1, it's a morphism into a1, and I'm going to show that this f is a constant, okay, I'm going to show f is a constant. And how am I going to do that? I'm going to do the following thing, I'm going to show that f satisfies I'm going to show f satisfies a monic polynomial with coefficients in k, okay, I'm going to show f satisfies a monic polynomial with coefficients in k, okay. That means if you consider everything as being inside this field, this is a field extension of k, this is k is a field, this is also a bigger field, and this is a field extension of k, and this is an element there, and beautiful thing is that this is algebraic over k. If I prove that f satisfies a monic polynomial with coefficients in k, I am just saying that f is algebraic over k, but k is algebraically closed, therefore f has to belong to k, and that is how I prove f is equal to some constant, okay. So this is how I am going to do it, and how am I going to get a monic polynomial that f satisfies with coefficients in k? What I am going to do is I am going to look at this ring, so I am going to look at Sy, I am going to look at polynomials in f, okay, which is also sitting inside this. I am going to look at this ring, this is the polynomial, I am writing polynomials in f with Sy coefficients, okay, I am going to study this ring, okay. So this is the broad idea of the proof, alright. So now let us get to the details. So so the first thing I want to say is, well, you see y is y is of course inside Pn, and Pn is the union of all these ui's I equal to 0 to n, these where each ui inside Pn this corresponds to the coordinate xi not vanishing, okay. So this is the affine piece which is isomorphic to an. So in fact that there is this isomorphism phi of this with an, you have this, and then I have y intersection ui inside this. So well, this is open, this is open, this is closed, this is closed, this diagram commutes, well this is irreducible, well this is also irreducible, okay. Of course, and here also this is also irreducible, that is also irreducible, okay. So this is your diagram, and the whole point is that we know what see see this isomorphism is how we showed that ui is actually affine. We proved that ui is actually isomorphic to affine space, therefore ui is affine, and this is an irreducible closed subset of ui, therefore this is also an affine variety, okay. And therefore we have that O of y intersection ui is just the same as A of y intersection ui, because y intersection ui is affine. And what is this? This guy, this is just, we know what it is. It's just s y, well you localize at xi and then take the degree 0 part. This is what it is. Okay, so this is affine coordinate ring of yi. Okay, so you take sy, you localize at xi. Okay, when you, because you localize at xi means you invert powers of xi. Okay, and xi is of course homogeneous of degree 1. Therefore when you invert powers of xi, there is a natural gradation on this, and then I am saying take degree 0 part, which means that you are just looking at some homogeneous polynomial in sy, okay, mod xi to the power of degree of that polynomial. That's all, that's what you are looking at, that's what this thing is. Okay, so so now what you should realize is that, you see, thus f, if you take f and restrict it to y intersection ui, this will belong to O of y intersection ui, because you take a regular function and restrict it to an open set, you will get a regular function, alright. But O of y intersection ui is this, so this implies is of the form, well it's an element here, so it will look like gi divided by xi to the power of ni, where ni is equal to degree gi, gi belonging to sy sub ni. This is the homogeneous part of degree ni in sy. Okay, mind you, see, I wanted to, let me again recall, see this is a homogeneous, this is a graded ring, so this is a direct sum of j greater than or equal to 0 s pn k j, where sj consists of homogeneous polynomials of degree j and s0 is going to be k, homogeneous polynomials of degree 0, alright. And this is just the standard fact that any polynomial can be broken down into its homogeneous components, and those homogeneous components are unique, and each homogeneous component has a homogeneous degree. Okay, so the polynomial has first degree 0 homogeneous component, which is the constant term, then it is a degree 1 homogeneous component, which is the linear term, then you have degree 2 homogeneous component, which is the quadratic term, and then the cubic term, and so on, and that is this decomposition, alright. And this decomposition also gives you a decomposition here. Okay, you are also going to get a decomposition of this ring. Okay, the only thing is that you read everything modulo this ideal, it's a homogeneous ideal, that's the whole point. So in particular, if you take a polynomial here, if you take a polynomial in iy, okay, that will go to 0 here. So if you take a polynomial in iy which is homogeneous of some positive degree, it will, suppose it has degree j, it will be in sj, but if you go to the quotient it will become degree 0, because you have read it, you have to read whatever you get, you have to read it mod iy. Okay, so you have this induced gradation here, alright. And so I think by notation I should use not s, so I should use s sub ni. Okay, so every element here is going to look, see, without this 0 it is going to look like some element of sy modulo some power of xi, and of course this gi is actually being read mod iy, mind you. Okay, if you want, actually I should put gi bar, but I won't do it. Okay, gi is just the image of a gi here, and I have to read it mod iy, alright. So it is going to look like this, and the point is, since I am taking degree 0 part, the gi is homogeneous of degree ni, and the denominator is also written so that the power of xi becomes ni, so that the denominator is also homogeneous of degree ni, so the induced degree is going to be 0, that is how it is adjusted, alright. Now this is how f restricted to y intersection ui looks like, alright. In fact, you know, if I'm just trying to say, think of gi as a degree ni homogeneous polynomial, okay. Then if you take this quotient, I have a degree ni homogeneous polynomial divided by another degree ni homogeneous polynomial, it is a quotient of two homogeneous polynomials. So this is certainly a regular function, and this regular function will live on ui, in fact, okay. This is a regular function that will live on ui, because I shouldn't say the whole projective space, it will live on ui, alright. So I want to make the following statement. You see this oy, so f is in oy, but you know, so let me try do something here. So you know, this is contained in O of y intersection ui, okay, because you know this is something that we have already seen. If you have regular functions on an open set, then you can restrict them to a further smaller open set, okay, and the restriction map from a regular function on a larger open set to a regular function on a smaller open set is an injective map, because the injectivity is because if two regular functions coincide on some open set, they coincide everywhere, okay. Therefore this is contained inside this, and you know, I started with an f here, okay, and what is the image of this f? The image of f under this inclusion is f is precisely f restricted to y intersection ui, okay. So I need some more space here, so let me write it correctly. Okay, so f goes to f restricted to y intersection ui, but the point I'm going to do something now. What I'm going to say is I'm going to identify these as these two together. I'm going to identify these two thinking that everything is happening here. So this is my big field where everything is happening, all things are happening here, okay. So everything is happening in this big field, which is the quotient field of sy, okay. So there is no difference between this and this after all, because this element f of f restricted to y intersection ui is just coming from this f, okay, which is a subset of this, and when I consider everything here, mind you, this is my universe, this is the big field where everything lives. So you know, I'm going to identify this with this, it's correct, alright. Now what I want you to understand is, you know, if f restricted to this is this, then xi power ni multiplied by f can be identified with gi, which is here, okay. So I'm going to write this xi power ni, okay, times f belongs to s ni y, okay. This is true for every I, alright. And in fact, you know what I should write is, if you want xi to the ni, f restricted to y intersection ui, okay, that's what I should write, but I am identifying f with f restricted to y intersection ui because everything is sitting inside this huge field and this element goes to that, okay, alright. Now, so you know, but what you should understand is that, you know, you see, if I instead of ui, if I take uj, okay, then I will get O of y intersection uj, alright, and well the f will also go to f restricted to y intersection uj, but then the fact is both of them, this f restricted to y intersection ui and f restricted to y intersection uj they will correspond to the same element here. That's something that you should not forget, okay. So even as the I changes, these things change, but they all come from the same f, so they all as I changes, the various f restricted to y intersection ui are all one and the same element here. I am calling them just as f, okay. So this is a small thing that you have to, set theoretic thing, that subtlety you have to notice, okay. Now, okay, so I have this. Now I'm going to play with this, and I'm going to say the following thing. I'm going to say that, you see, you know, basically the idea is f is a regular function. See, a regular function on a projective variety or a quasi projective variety is just a quotient of two homogeneous polynomials of the same degree. So essentially it is degree 0. You see, you must understand that it is degree 0 if you think of it as locally as a quotient of two homogeneous polynomials of the same degree, which is what it is. It's a degree 0 object, and this so you know, this is correct to expect. You take a degree 0 thing, you multiply it with degree ni, the resulting thing is of degree ni. It lands in the piece with which consists of homogeneous elements of degree ni. So this statement is correct, alright, I mean it's believable. Now what I want to do is put n is equal to sigma ni, take the sum of all those ni's, okay. Consider, take any m greater than n, greater than or equal to n, okay. Take any monomial in x naught dot 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 x naught and so on up to xn of degree m, okay. So this monomial will look like x naught power m1 into x naught power m2 and so on x naught power mn with sum of all the mi's equal to m. This is how a monomial in all the xi's of degree m will look like, alright. Oops, is something wrong? Okay, I'm oops, this should be 1, this should be n, maybe this should be 0, my numbering is bad, okay, right, alright. So this is how a monomial of degree m looks like, and the point is you multiply a monomial of degree m with m greater than n with f and you will again land inside degree m piece because of this observation. Now you see x naught to the power of m naught xn to the power of mn times f if I calculate, okay. See this is, you must understand that there, since m is greater than or equal to n which is sigma ni, okay. See there exists j such that you know mj is greater than or equal to the corresponding nj. This has to happen because if every mj, small mj is less than, strictly less than capital Nj, then the sum of all the small mj's which is m has to be strictly less than the sum of all the n's nj's which is n, whereas I have assumed m is greater than or equal to n. So this is it's an obvious thing that has to happen. So then you know I can write this as x naught power m naught blah blah blah, then you know when xj comes I will put mj minus nj, then I will write xj plus 1 blah 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 power mj plus 1 and go on up to xn mn. I will take out this xj power nj times f, and I know this xj power nj times f is in s sub njy, this is in s sub nj, okay. So this is a degree nj homogeneous object, okay, it is a degree nj homogeneous polynomial, and what is left out is a homogeneous polynomial of degree m minus nj. So the moral of the story is that this whole thing is going to lie in s m y, okay. This is what happens because this fellow lies in, this belongs to s njy, that is because of this observation, okay. So this part is homogeneous of degree nj, the remaining part is a monomial of which is homogeneous of degree m minus nj, okay. Therefore when you multiply it you will get the total degree will be m minus nj plus nj, so you will land in m, okay. Now this happens for every monomial of degree m, okay, but all these monomials of degree m, what do they span? They span precisely Sm, okay. After all Sm is the space of all homogeneous polynomials of degree m, of course red mod iy, because you are in Sy, you are not in S of Pn, okay, you are in S of Iy. Therefore the moral of the story is that since such monomials span S m y, we have Smy dot f goes into Smy, okay, you have this. You take an element of Smy multiply by f, you end up inside Smy, okay, because any element of Smy is just a linear combination of k linear combination of such finite linear combination of such monomials, and each monomial is going to push f into Smy, alright. So you are going to get this, and now from this what you can get is that Smy of f squared will go into Smy of f dot f, which will go into Smy dot f, which will go into Smy, and if you continue by induction you will get Smy will take f power r into Smy, okay. So multiplication on the right by powers of f, non-negative powers of f, is going to push Smy into itself, okay. So you have this, so so in particular what I want you to notice is that if you take x naught power so I want to, so here is the observation that is very important for us. The observation is that S y f, okay, I want to say S y f is contained in x naught to the power of minus n times Sy. So here is the important observation. I mean it's a that is a result of this actually, okay. See and where is all this happening? This is all, mind you, all this is happening in the quotient field of Sy, the big huge field where everything is contained, it is happening there. See, x naught to the minus n makes sense there in the quotient field of Sy, okay. So everything is working there, everything is living there, right. Why is this true? That is, this is because you see you take any homogeneous piece here, I mean you take any element here and multiply by f, and if you further multiply by x naught power n, the result is going to go into Sy, okay. See any element here is going to look like sigma hi f power I equal to 0 to some L. This is how something is going to look like, and you see this each hi is in Sy, okay. But now if I multiply outside by x naught power n, okay, if I multiply outside by x naught power n, then this thing, if this x naught power n into hi will push each homogeneous component of hi into a degree greater than or equal to n, okay. See each hi is in Sy, alright, each hi is in Sy, so each hi breaks down into homogeneous components, and it could have components from degree 0 onwards up to some value, finite value, but multiplying by x naught power n hikes all these degrees of these homogeneous components to make even the minimum to be greater than or equal to n, okay. Therefore when I multiply by x naught, this goes into Sy because of this observation. Whenever you take any homogeneous degree greater than or equal to small n, I mean degree greater than or equal to capital N polynomial, and you multiply by any power of f, you again get degree greater than or equal to I mean you again get a homogeneous polynomial mod I y. So this goes into this, therefore this is in x naught power minus n, that it implies that any polynomial in the f with coefficients in Sy, this belongs to x naught to the minus n Sy. So that is how you get this in here. Okay, now the nice thing is so the moral of the story is, you see, this fellow here is actually contained. So what I've got is that this fellow is actually contained in x naught to the minus n sy, which is of course also contained here. Okay, so this, see this object, this polynomial ring in f with coefficients in sy, this is caught inside this, and we are more or less done. You know why? The fact is because, you see, this fellow here, this is as a now think of everything as an sy module. This is a finite, this is a sy module generated by the single element x naught to the minus n. X naught to the minus n sy is the sy module, is the sy submodule of the quotient field of sy generated by x naught to the minus n. Okay, so it's a module which is generated by a single element, so it's a finitely generated module. Okay, and sy is what? Sy is a Noetherian ring. This is a finitely generated module over a Noetherian ring, and this is a submodule of that, therefore this is also finitely generated. Okay, so you see sy since it is generated by one element, it is finitely generated over S as sy module, and since sy is Noetherian, so this is where we are using the fact that the polynomial ring is Noetherian. See, the polynomial ring is Noetherian and sy is just a quotient of a Noetherian ring. A quotient of a Noetherian ring is also a Noetherian. Therefore sy is a Noetherian ring, and you have a finitely generated any finitely generated module over a Noetherian ring is also Noetherian, and every submodule of a finitely generated module over a Noetherian ring is also Noetherian, is also finitely generated. Okay, so the final conclusion is that sy of f is finitely generated as a module over sy. This is what I want. Okay, now you know, now we go into a little bit of commutative algebra. You see, the fact that syf is finitely generated as a module over sy is equivalent to saying that f is integral over sy. Okay, that is that f satisfies a monic polynomial with coefficients in sy. Okay, by the commutative algebra of integral extensions syf is an integral extension of sy. F is actually integral over sy. Okay, and f is integral over sy. So this is some commutative algebra which you can I mean you can easily look up in a book on commutative algebra. For example, standard reference is Atiyah and McDonald's Introduction to Commutative Algebra. You look at the chapter on integral extensions and you will find this, and it's very easy to prove. It's just an argument that involves some determinants. Okay, so by the commutative algebra of integral extensions, f is integral over sy, that is f satisfies a monic polynomial with sy coefficients. So you know you will get something like this, you will get f power t plus a t minus 1 f to the t minus 1 plus blah 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 plus a not equal to 0, okay, where the ai are actually in Sy, and this is all happening in the quotient field of Sy, mind you, this is all happening in this quotient field of Sy is a huge extension field of K, it is a huge extension field of K. In fact, you know, this itself is a huge extension of K, because you know actually this is the quotient field of Y, its transcendence degree over K is actually equal to the dimension of the variety Y. So if Y, see Y is inside Pn, okay, so Y can have at most dimension n, if it has dimension n it is it's all of Pn, otherwise it will have lesser dimension, but suppose Y has dimension R, then this quotient, the transcend, it means that this field extension, the quotient field of, or the function field of Y, its transcendence degree over K is equal to dimension of Y, so this is a huge field extension, okay, this contains a lot of transcendental elements. So this itself is a huge field extension, it is a transcendental extension, and this is a much more huger one, okay, so everything is happening in that huge field, okay. Now you see, now each of these a sub i's, they are in Sy, so they have homogeneous components, and what I want to say is that you can write out, you can replace each of these with the degree 0 homogeneous component, okay, and so what you do is now multiply this whole thing throughout by x naught to the n, right, so you will get x naught to the n f plus x naught to the I mean a n minus 1 a t f to the t e plus a t minus 1 x naught to the power of n f t minus 1 plus dot 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 x naught to the power of n times a naught is 0. Now this certainly makes sense inside, so this makes sense inside Sy, okay, that is because you know x naught multiplying f by any homogeneous polynomial of degree greater than or equal to capital N pushes it into Sy, that's the whole point here. You multiply any power of f by any homogeneous polynomial, or even any polynomial with the condition that every homogeneous component has degree greater than capital N, then the result will land inside Sy. So this happens in Sy, okay. Now once this happens in Sy has a gradation, if something is 0 then every graded piece is 0, so if you take the degree 0 part, so you know you take the degree x naught power n part of this, which is the lowest degree, if you take the degree x naught power n part, then what I will get is I will get this, I will get x naught power n ft plus a t minus 1, and you know I am going to put 0 here to tell you that a t minus 1 0 is the degree 0 part of a t minus 1. See each a t minus 1 is in Sy, and since Sy has a gradation, a t minus 1 breaks down into various parts of homogeneous parts of various homogeneous degrees, and I am taking the degree 0 part, then I will get x naught to the n f to the t minus 1 plus and so on, and then finally the last time I will get is x naught to the power of n a0 upper 0, this a0 upper 0 is the degree 0 part of a0, I will get this is also equal to 0, okay, and where and this will happen in Sn y, this will happen in the degree 0 piece, in the degree n piece, okay. This is because, mind you, whenever you have a graded ring, an element in that ring is 0 if and only if every homogeneous piece is 0. So this element on the left side is an element of Sy, which is a graded ring. The fact that it is equal to 0 means that each of its homogeneous pieces is of degree 0, and what is the minimum degree homogeneous piece? The minimum degree homogeneous piece is capital N, okay. So I am taking the degree, I should not say degree x naught to the power of n, I should say degree n, I am taking the degree n part, okay, the lowest degree part. So I end up with this, alright. Now what I will do is I will cancel this x naught to the n, and when I cancel into x0 to the n I have to go out of this, but I will still be in the quotient field of Sy. So this implies that ft plus a0 t minus 1 f to the t minus 1 plus blah 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 plus a0 0 is equal to 0 in the quotient field of Sy. So this makes sense because I am just multiplying by, I am simply multiplying by x0 power minus n, which throws me out of Sy, but certainly keeps me inside this quotient field of Sy because x0 to the minus n lives there, alright. But after all, what are these guys? What are all these a t minus 1 0? What are all those things? They are all scalars, they are all constants, they are degree 0 polynomials. See, they are degree 0 aj 0 belong to S0y. This is a degree 0 polynomials, red mod iy, and this is just k. This is just k, and so this implies that f is algebraic over k, but k is algebraically closed. So f belongs to k. So this implies O of y, it goes into k, which means that O of y is equal to k, and that is the end of the proof. Okay. So finally I ended up showing that every fellow here is actually here. I end up showing that every regular function small f in Oy is actually in here. So that means that this is actually equal to this. Okay. So the only thing that you will have to look up in commutative algebra is this integrality, which I think is very easy to understand. It's a small exercise. You can look it up very clearly in Atiyah McDonald's book, Introduction to Commutative Algebra. Okay. But anyway, the moral of the story is that there are no non-constant regular functions on a projective variety. Okay. So I will stop here.